Let's make an atom of iron by listing the correct number of each of the subatomic particles. The subatomic particles are protons, electrons, and neutrons, all of which have a certain mass and charge. We're one step closer to figuring this out, but let's keep gathering more information. Since iron is the element of interest, we look at the periodic table and see that it has a 26 in the corner of its elemental box. That number is called the atomic number, and it's 26 for iron. But how is that useful to the problem of interest? Well, it turns out that atomic number and proton number are synonymous. They're the exact same thing. Therefore, if we have the element of iron, we have 26 protons. That's because atomic number is what distinguishes and identifies the element of interest. For example, if oxygen has an atomic number of 8, that also means it has 8 protons. Conversely, any element with 9 protons must be fluorine. Okay, but what about the other subatomic particles? How many neutrons and electrons do we have? Well, remember, we have an atom of iron specifically. An element is an umbrella term that includes atom, ion, and isotope. Iron is an element defined by 26 protons, and we can have an atom of iron, an ion of iron, or an isotope of iron, all with 26 protons. Since the question of interest specifies an atom of iron, the definition of atom in general is that the number of protons equals the number of electrons. Therefore, if we already know that there's 26 protons and that protons and electrons are equal to each other, there's got to be 26 electrons. If A equals B equals C, A must equal C. But what about neutrons? The definition of atom makes no mention of neutrons, so what does that mean for an atom of iron? The interesting thing is that neutrons could be any positive whole number because neutron count is irrelevant when defining and describing an atom. The only thing that matters when determining whether or not we have an atom is if the number of electrons and protons are the same. Neutrons may or may not be equal. Now, neutrons can and do vary, but that's when we talk about isotopes. It's not relevant for atoms. With that, however, I do want you to take note of this. What we see here, 26, 104, 26, technically speaking, fits the definition of an atom because protons equals electrons. However, in practice, having 4 times as many neutrons would be far too unstable to exist in nature. But definitionally, it's still an atom. Be sure to check out the best video of all time on subatomic particles and the elements they form.